So remember, this whole unit's about differentials, right? And slope fields gave me a way to be, okay, let me back up. Differentials, sometimes we can solve them using our integration rules. A lot of times we can't, but I can at least give you a family, and that's what slope fields for. And what I mean by solving is finding the original function, because a differential equation has the original function in it, kind of treated as an unknown variable, and some form of its derivative, first, second derivative, also treated as an unknown, maybe some form of a variable. So there are two unknowns a lot of times. So that's what a differential equation is, okay? Like this, right? We got the original function and we got the derivative in it, so it's a differential. So we started off by practicing some easy ones. Hey, is this a solution to this differential that makes it work? And then how do I actually find the family of functions? And that's what slope fields were. Hey, I can tell you what they're going to look like, and if you give me a little bit more information, I can probably tell you, hey, it's going to be this one out of all these possibilities. And then we could get some exact solutions if we can separate variables. We did that. And so we're going to look at some exponential models with differential equations, something you've seen before, okay? So in many of our natural sciences and in the real world, quantities tend to grow or decay at a rate proportional to their size at any one time, like, you know, rabbit populations, bacterial populations, human populations, money, things like that. The rate of change of y with respect to time would look like this. So the rate of change of y with respect to time would look like this, where k is going to be some sort of constant. Okay, that's how it's changing. And y might be its size. So if you think about money, and you're going to earn 5% on your money, it's going to be 5% of what? Whatever the amount of money is. And I'm going to argue, you've played with this before. I'm going to show you something here. Okay, so if I've got something of this nature, dy, dt, dy, dx, whatever it is, equals some constant y, that could be exponential growth or exponential decay. I'm going to show you this. Let's solve this differential equation. Maybe I should just, I was trying to make it really big so it would show up, but no, it's not showing up. It's showing up. I wanted everything to show up. Let's see. Yeah, that looks pretty much like everything. I'll walk through it with you. All I have to do is, we can see. Okay. All I have to do is put the original, so dy dt. Right, that's what we had originally. And I noticed, you know what, I can probably separate these variables. Right? So that's what I'm doing here, moving the y over here and multiplying the dt over here, and I get that. Right? Separate the variables. And I get this, I got all the y's on one side, I got all the other variable, in this case t, on the other side. And then I integrate each side. Right? Okay. When I integrate each side, I get the natural log, because I got 1 over y. So the integral of that is natural log of y. And that's going to be kt. And then I get a constant here and a constant here, but this constant's going to end up moving over here with this. So I get a constant. right? So this is what it is when I integrate. But then I want to see, hey, can I isolate the y, which is right here? And so if I look for ways to isolate the y, which is an argument here, one thing I could do is I could raise each side by this power, e to that power. Why e to that power? Well, because there's a natural log here, and that's log base e. And so e raised to the natural log base e is just going to be y. Like if that were 3 log base 3, it would be y. So if that base and that base are the same, your exponential base and the original base are the same. I don't know if you remember that from algebra 2, but then your answer is just the arguments there. So I'm going to choose e raised to that power. Whatever I do to one side, I got to do the other. E raised to that power. Okay, got to do it because I did this side. I'm picking e because it's the same base. There's an e there. And then that just becomes y. Well, then over here I got this. But at least I isolated the y. Y equals e to the kt plus c. And I know that if I'm adding exponents here, I probably started out with the same base being multiplied. E to the c times e to the kt equals e to the kt plus c. Well, how is this any better than that? I mean, probably in algebra 2 you were told this was better than this because you got the one base and you're just adding exponents. This seemed to be better. Well, the reason is if I split it up like this, same base multiplied this, that. E to the c power is just a constant. It's just going to be a number. And so I got y, in this case, absolute value of y, equals c times e to the kt. Okay. Why is that important? Oh, because you've seen this before. PERT. Compound interest, or actually you saw it this way. Sorry, you saw this, right? Amortized amount equals P. You saw that when you were doing compound interest. This was the rate at which money grows, that was the amount of time. This is the rate at which population is changing, or your money's growing. That's the time. E raised to that. P is principal, so you know what C is? It's the initial amount. When time is 0, because when time is 0, what is e to the, I don't care what that number is, times 0. 1. So when time is 0, I just have C, so that's what you're starting out with. That's what you start out with. And you've used this before. So, what I'm saying with all this is that is going to be a solution to everything that looks like this. Everything that grows or decays exponentially is a solution to this. Everything. And now I'm showing, I just showed you why it was. You just proved it. Okay. So you've used it before, and you're going to use it again. Maybe not necessarily with money. We could use it with money, but I think you've already used it with money. So that's what I'm saying here. An exponential function of the form y equals c times e to the kt satisfies any differential that looks like this. So your initial quantity, initial population, initial amount of money, initial whatever is C. Sometimes you have to figure out what C is, but that's what it is. And on the AP, look for questions with the phrase the rate of change. Oh, rate of change. That's derivative, dy dx. Proportional to. Is equal. Look for something the rate of change is proportional to. That means something multiplied. Something multiplied like this. Something multiplied. So that kind of tells you, I can set up this, and I know what the solution to this is. Right there, sorry, I'm pointing all over the place. I know that the rate of change of something proportional to is this, and this would be a solution to it. Okay, let's try it, right? Might as well try it. So let me scroll. 1, 2, 3, 4. Got some examples to do. So dy dx equals 2y and y equals 1 when x is 0. What is the value of x when y is 3? Well, you know what I notice here? Dy dx equals k. I would argue it's already in that form.
So could you just put it to the other form?
Yeah. I don't have to separate the variables. I mean, you can. You can separate the variables and then integrate both sides and get y equal to, but we already did that, right? If it's of this form, I can do all that, but I already know I'm gonna end up getting those. I already know I'm gonna get that.
Equals 1 when x equals 0.
Yeah, so,
Initial.
gonna prove to you. I bet that's gonna be 1. So let's see, when y is 1, when C, E, what is K?
2.
Yeah, look, we got K. K. There's K. 2t. Well, now we know t is 0.
So we know C is.
So that's just gonna be 1.
C equals 1.
But also, we would have known that, hey, when x is 0, the initial amount is 1. We could have said, hey, because of this, they gave me x is 0. That is what C is gonna be. Okay, they're already giving me the initial amount. Okay, so what I have here, y equals, I know C now is 1. E, I know K is 2 because it's in this form too. Yeah, I put it in that form. I probably should have had the x there, sorry. This was x, not t. Sorry for that little 2x. So apparently it's doubling, but it's dependent on the size. Something is doubling, right? And it starts out at a value of 1. So what's the value of x when y is 3? E to the 2x, 3 equals e to the 2x, 1 times e to the 2x. If it wasn't 1, it'd be whatever. And so you probably have to divide that over there, which we will.
Put it back in natural log.
You're probably going to want a natural log both sides, because the only way to get a variable down from the exponent is to take the log of both sides. And I'm probably going to want to use log base e, because again, that gives me, so I'm looking at this side right here. Probably going to natural log that side, because that's base e, it just leaves that. And then whatever I do this side, I got to do this side. So that's just going to bring down the 2x. I got natural log of e raised to what power is e? That's just going to be 1. I mean, you could have chosen a different log, but choose the same base as the base. I used to tell that to my pre-cal, choose the same base as the base. And let's see, x will divide by 2. Natural log of 3 divided by 2 is x. You can leave it like that if you want to, because the rest is just arithmetic. We got it. We got a solution. We knew what the solution was going to be because we already worked out how to find the solution. Questions on that? No questions from halfway around the world? No? Hey, let's look at number 2 then. Number 2, multi-guess. Well, there's some ways you could do the multi-guess without maybe doing it this way, but since we're in this section, we're gonna do it this way. So let's try to show everything up there at one time. Okay, oh no. There we go. Okay. Population y grows by the equation dy dt equals kt, where k is a constant and t is measured in years. The population is going to double every 10 years. Then what's the value of k? Oh, now we're trying to find the value of k. But I notice I've got this, right? So I know this is going to be a solution. Sometimes k is called the constant of proportionality. And we don't want to call it, hey, that's another constant. Well, it's not going to change. But, what am I going to do here? It does look like I have a lot of variables up there.
2 times 2 is equal to.
It doubles every 10 years.
So k times t needs to equal 2, right?
I'm going to say this. In order to get that, so I can solve for k, I probably need to get that first. So k I'm not going to solve for first, but in 10 years, whatever this one is, the initial amount will have been doubled in 10 years. I'm going to argue, I don't think it really matters what this is, because you're probably going to end up dividing it anyway. Doesn't matter what this is, just make sure that's double. Because when t is 10, this will have been doubled. So, what do you want to use? Yeah, let's say you didn't want to use it. Let's say you wanted to use 160 later, it became 160, it was double. Guess what's gonna happen? You're gonna divide by 80. You're gonna get 2 anyway. So it doesn't really matter what you choose, as long as you make it double. So, choose easy numbers. So I got that. Okay, so even if I had a number here that wasn't 1, I would divide it over here. This would end up being 2 anyway. 2 equals e to the kt. Or let's call it 10k. Is that easier? Make it 10k better. Well, now I'm trying to find k.
Natural log.
Yeah, why not use a log that has that same base, ln? Because then I'm gonna bring that down. Well, that means I gotta do this side. So I get ln 2 equals 10k ln e, and that's just gonna be 1, which is why I chose ln 2 over here. And so I think k is going to be natural log of 2 divided 10 over. Oh, I don't see that as one of my answers. So I'm thinking, obviously, this would have been on the computer part, or the calculator part. So what is the natural log of 2 divided by 10? Probably, you know, AP loves 3 decimal places. What'd you get?
0.03.
It's not one of our answers. Did you do natural log 2 divided by?
Oh, I did. My fault. 0.069.
Oh, that's the first one, right?
Yeah.
You're right. You're right. And again, you could have plugged in any numbers as long as you read the problem and said it doubled after 10 years.
Could you explain again why you can put any number, like what do the ones say?
Yeah, let's say you didn't want this. I know the initial amount had to have doubled if t was 10. I know that because that's what, the population doubles every 10 years. So if t is 10, whatever this says, 10 years later, will be double. Give me any number you want.
Oh, so if you put 27.
27. That's the initial amount.
Yeah.
So in 10 years' time, this 27 will be 54.
Okay.
And then what you would have just had another step right there. You would have done 54 divided by 27 equals e to the 10. And so that's 2 equals e to the 10. So I would have gotten 2 anyway. So that's not a magic number.
Okay.
I didn't pick 2 and 1 because it was magic. You know, it might say, hey, if it was decay, it might say it's half as big 7 years from now. Well, then pick a number and then pick half of it 7 years from now.
Okay.
Do it that way.
That makes sense.
You can pick anything you want.
I'll be back after that.
Yeah. Or it might say it triples in size, something like that. Just make sure initially, whatever number you pick, this number is now 3 times the size. And whatever amount of time they set it to. Sometimes they might say, hey, every 6 months, so t is actually 0.5. Half a year.
Okay. That makes sense.
Okay. Is the next one a multi-guess one?
Yeah.
We'll let the next one be our last one of the day. So, let's see. Oh, dy dx equals 4y and y is 4 when x is 0, then y must equal, oh, this one's, I would argue with this one, we may not even need much. Because I'm looking at this and I see this. Although you can mark it. dy dx equals k bar. I see that form right there. So I know y equals c e to the k x instead of t this time. Right? I really only see one option that has that form. It ain't that one, it ain't that one, it ain't that one. And when x is 0, y is 4 when x is 0, so I immediately know there's a 4 here, not a 1. Man, the only thing, I don't even have to figure out anything else. It's this one. That's the only one it could be. That's 1, 2, 3. Hey, we'll say 4 for tomorrow. Which is not as bad as it looks, just because it has words in it doesn't make it bad. It's actually pretty easy. I mean, you could keep going and figure out what k is, but there's only going to be one that's going to match.